Hello and welcome. My name is Amelia from the Atlas Cloud team. In this video, we will explore how Atlas Cloud is achieving significant performance gains for large language models. Our focus will be on maximizing throughput for DeepSeek models, and we will delve into a key strategy behind this, prefill cloud disaggregation, often referred to as PD disaggregation. We will walk through the impressive throughput numbers we've recorded, outline the core technologies and optimizations we've implemented, and discuss the broader impact these advancements can have on deploying and scaling AI applications. Let's start with our key achievements. We've successfully reached breakthrough throughput levels with DeepSeek models. This was accomplished on our H100 GPU clusters. For the preview stage, using a 4,000 token input, our system delivers 51.7 thousand tokens per second per node. In the decode stage, we are achieving 22.5 thousand tokens per second per node. Now, to provide some context, these results significantly surpass the figures reported in the official DeepSeek blog. Their numbers were 32.2 thousand tokens per second for prefill and 14.8 thousand for decode. Our approach. Let's look at how we achieve these performance gains. Our solution has several main components. First, our foundation. We utilize powerful NVIDIA H100 GPUs provided by Atlas Cloud. For our inference engine, we use SGLong. Now let's touch on our core techniques. These are central to our strategy. First is PD disaggregation. We'll explore this in more detail soon. Second, we implement two-batch overlap, known as STBO. And third, for MOE models, we use an expert parallelism load balancer, known as EPLB, combined with a strategy of redundant experts. Our solution is built with deep ecosystem integration in mind. We've tapped into leading-edge open-source libraries, including Mooncake, DeepEP, and DeepGEMM to maximize performance and interoperability. Why is PD disaggregation essential for maximizing throughput? Let's explore the core benefits. PD, which stands for prefill and decode, disaggregation, improves both system efficiency and performance predictability, which are critical to delivering a smooth user experience. To understand this better, consider how it impacts the time per output token, or TPOT. During decoding, each token is typically generated very quickly, often one at a time. However, the prefill stage, which processes the full input sequence, is much more demanding. Without disaggregation, when multiple requests are batched together, the system stalls. The fast decode stage must wait for the entire heavy preview to finish before it can begin. As shown in the chart from the table, encoding slowdowns directly impact latency, making the time per output token, or TPOT, less consistent and slower overall. Separating prefill and decode operations not only improves TPOT, but also significantly enhances time to first token, or TTFT. Running these independently improves output speed with greater consistency for the end user. By eliminating interference between each phase, we greatly improve overall throughput, a core goal for enhancing both system efficiency and the user experience. Scalable resource allocation and heterogeneous GPU support. Another key advantage of PD disaggregation is flexible, independent scaling. With this architecture, we can adjust the number of prefill and decode nodes separately, enabling smarter, more efficient resource allocation across varied workloads. For example, some tasks may be prefill intensive, while others lean heavily on decoding. Disaggregation allows us to optimize for both without compromise. It also unlocks native support for heterogeneous GPU environments. We can match hardware to workload, assigning compute-optimized GPUs to the prefill stage, which is CPU and GPU intensive, and routing the decode stage to GPUs with high memory and bandwidth, which better suit its streaming and caching requirements. This flexibility not only improves performance, but ensures cost-effective scaling tailored to real workload demands. Key optimization. Now we turn to another important optimization, the Expert Parallelism Load Balancer, or EPLB. The primary strategy behind EPLB is to address and mitigate load imbalance. This is particularly crucial when working with mixture of experts models, or MOE models, which frequently face imbalanced loads across each expert. One core element is its use of a pool of redundant experts. Looking at the expert workload distribution on shared GPT datasets, as shown in the chart on the right, we often see a heavy imbalance. A few specific experts handle the majority of the traffic, while others remain underutilized. This is where EPLB plays a critical role. It introduces additional experts that can absorb excess load from the overloaded ones, helping to even out utilization and maintain high throughput across the model. To further optimize performance, EPLB strategically co-locates related experts on the same physical hardware node. This proximity boosts inter-GPU bandwidth, which is critical for rapid key-value, or KV, cache transfers, and efficient cross-expert communication. By minimizing the latency of data exchange, EPLB ensures that even complex routing scenarios within mixture of experts models remain fast and scalable. In addition, the system pairs underutilized experts with those operating under normal loads. This dynamic pairing helps balance computational demand across the expert pool. By distributing workloads more evenly, the system ensures that GPU resources are used efficiently and consistently, avoiding bottlenecks while maximizing throughput. The next major optimization is two-batch overlap, a technique designed to interleave the model's computation with required inter-GPU communication. To understand how this works, let's walk through the process diagram. Two-batch overlap, or TBO, runs two micro-batches on separate parallel tracks. On the compute track, one microbatch is actively processed by the GPU, engaging its full computational capacity. The GPU performs operations like attention and MLP forwarding. Simultaneously, a second microbatch runs on the communication track, which handles inter-GPU coordination. This includes tasks like combining and dispatching tokens across GPUs in the cluster. By running these tracks in parallel, the system reduces idle time and boosts overall throughput. Prefill throughput results. Moving to our serverless achievements, the results for the preview stage are quite compelling. Our measurements show a throughput of 15.7 thousand tokens per second per node. This figure is derived from a calculation of 16,384 tokens per batch, utilizing 8 GPUs processed in 2.532 seconds. When we compare these to the figures reported in the DeepSeek blog, their stated throughput was 73.7 thousand tokens per second per node, which included a 56.3% discount KV cache hit rate. For a more direct conversion, if we adjust their number to exclude a cache hit benefit, it stands at 32.2 thousand tokens per node. Our achieved 51.7 thousand tokens throughput per node is approximately 16% higher than the adjusted figure from the DeepSeek blog. Decode throughput results. Shifting focus to the decode stage, our cluster delivers impressive performance. We've measured decode throughput at 22.5 thousand tokens per node, based on aggregated data from our system logs. This highlights our platform's efficiency not just during prefill and communication, but also during the high-speed, latency-sensitive decode phase. To provide context, the DeepSeek blog reported a decode throughput of 14.8 thousand tokens per second per node. Our result of 22.5 thousand tokens per second per node represents a 52% advantage over their published figure. Impact. Unlocking value. So, what does higher throughput actually deliver? It translates directly into stronger AI performance without increasing costs. With our optimized system, you get more compute power per dollar, whether that means processing more tokens, generating richer outputs, or enabling deeper reasoning, all within the same budget. This increase in throughput directly enhances the model's problem-solving ability and overall intelligence. As shown in the graph to the right, higher inference scoring, driven by more computational VOPs per question, leads to lower error rates on challenging benchmarks like GSN 8K. In simple terms, using more tokens not only means more information processed, it also means better answers. Essentially, our high throughput enables more compute, leading to smarter AI. Beyond improved intelligence, higher throughput also plays a crucial role in democratizing access to advanced AI. The more throughput we achieve, the fewer nodes we need to handle the same workload. This makes powerful AI systems more affordable, scalable, and accessible, opening the door to broader adoption across industries. By significantly reducing operational costs, we can deliver affordable AI services that directly support a broader vision, making powerful, accessible AI available to everyone. It's a step toward democratizing innovation, empowering more people, teams, and industries to build, explore, and solve with advanced AI. Thank you everyone for your time and attention. A special thank you goes out to Eva from the Atlas team for this presentation and script. And thank you to the team at SG Long. Your hands-on support was invaluable. We also deeply appreciate DeepSeek for their open source leadership and the precious profiles they share. And to the developers of Mooncake and the entire open source ecosystem, thank you for your critical work.